Chapter 6 is called Chemical Bonding. Valence electrons are a very important part of chemical bonding because these are the electrons that are available to be lost, gained, or shared when you're actually making or forming a compound. So anytime you are bonding or creating a compound between two or more elements, it is dealing with the valence electrons. In order to determine the number of valence electrons, it is not a hard process. The group number will lead you to determine the number of valence electrons. Remember, the group number are the columns on the periodic table. Group 1 would have 1 valence electron, group 2 would have 2. We skip the transition metals, groups 3 to 12, and we go over to group 13, which would have 3, and likewise all the way to group 18, which would have 8. The max number of valence electrons an element can have is 8. It will never have any more than 8. It will never have any less than 1. So it'll always be from 1 to 8. Just a reminder what electronegativity is, because we will be getting into some values here. That's the measure of the ability of an atom to attract electrons. And there is the trend, in case you forget, from last chapter. We will see that noble gases do not have, for the most part, electronegativity values because they have a full octet. They have a full valence electron shell, so they do not want any more electrons. They do not want to give up any electrons. They do not want to bond at all. They are full. They are happy. That's why we ignore the noble gases, and that's group 18. There's the trend. Now, what is a chemical bond? You can see the definition there: mutual electrical attraction between the nuclei, which we know has protons and neutrons, and valence electrons, which we know are negative. So if we have positive in the nucleus, negative on the outside, it's that attraction. And it binds atoms together. Two types of bonding we're going to look at: ionic bonding and covalent bonding. Ionic bonding is bonding between cations and anions. Cations are ions of a metal. It is a positive ion. It has a plus charge. An anion are ions of a non-metal. This has a negative charge. So you can imagine the cation and the anion would be attracted to each other because of the opposite charges. That's ionic. It includes ions. Covalent bonding, on the other hand, is the sharing of electrons. This is between two nonmetals. This will be your molecules. Sugar, for example, has covalent bonding in it. The greater the difference in electronegativity values from chapter 5, the more ionic the bond is. So our electronegativity values can be found in the sheet I gave you. You do not have to memorize this. You would always have this available to you. So the difference between two elements, you take the difference, the greater the value, the more ionic. So we have ionic, we have covalent. We break down covalent a little further. Two types of covalent bonds. We have a nonpolar covalent bond and a polar covalent bond. A nonpolar covalent bond is when the bonding electrons are shared equally. That is an equal sharing. You should add the word equally there. That's very important. We'll use our table of electronegativity values, and we'll find the difference between two elements. If they have a difference of anywhere from 0 to 0.3, the bond is considered nonpolar. So there's equal. They have relatively equal electronegativity values. A polar covalent bond, on the other hand, has an unequal attraction for shared electrons. This is when two elements have pretty different electronegativity values. When you subtract the values, if you get anywhere from 0.3 to 1.7, that is considered a polar bond. Now, these values down here are not set in stone, and different textbooks have different ranges for this. But in general, we'll go with these ranges. The question comes, what if you have 0.3? And that's different depending on the case. I'll try not to give you any with 0.3. But you should know those ranges and the difference between polar and nonpolar. Again, nonpolar, you can see here at the top, it is an equal sharing. See how the cloud, the electron cloud, is the same size? It's equal. 2 carbons. If we took carbons values from your table, it's 2.5. And if we subtracted a carbon value, 2.5, we get 0. And 0 is obviously between 0 and 0.3. Polar, on the other hand, at the bottom, we have oxygen and hydrogen. Hydrogen is 2.1. Oxygen is 3.5, and if we subtract them, we get the range of a polar bond between 0.3 and 1.7. So there's an unequal sharing there. Oxygen wants the electrons more than hydrogen. If you would subtract the 2.1, do 2.1 minus 3.5, you get a negative 1.4. Just make it positive, okay? Just take the absolute value of that. It will always be positive. Notice there's no ranges for negative here, so it doesn't matter the order, just make it positive. Here's just very easy practice, just subtracting, just using that table again here. So the first one asks for chlorine and calcium. Chlorine is 3.0, calcium is 1.0. When we subtract, we get 2.0. Now you might be thinking, wait, that's greater than the 1.7. So would that be like polar, or what would that be? If it's above 1.7, a lot of times it'll be ionic. So remember, we have covalent bonding, we have ionic bonding. Under covalent, we have polar and nonpolar, and then ionic, we just have ionic. Remember, this is between a metal and a nonmetal, more specifically a cation and an anion. So notice here that we're dealing with chlorine, which is a nonmetal, and calcium, which is a metal. That's ionic. So do you always need to do the subtraction? Not necessarily. If you see a metal and a nonmetal, it's ionic. You don't even have to do subtraction. But we did just to prove the values. The next one says chlorine and oxygen. Chlorine minus oxygen. We're going to make it positive. 0.5, which would be polar. And the last one says chlorine and bromine. Bromine is 2.8. We get 0.2, which is nonpolar because it falls within the ranges of 0 and 0.3. Okay, molecular compounds. We've done this before. Just a review, molecules, a neutral group of atoms that are held together by covalent bonds. Your nonmetals will be here. Nonmetals. Sugar, all nonmetals, that's a molecule. The formula of something just tells us how many atoms we have of each element, obviously. So down here, we can look at H2O. That tells us we have 2 hydrogens and 1 oxygen. We don't show the 1. Two important vocab words with covalent bonds is bond length and bond energy. They mean pretty much what you think they mean. The distance between 2 bonded atoms is the bond length, the length of the bond. Bond energy is the energy required to break and form the bonds. Some bonds take more energy to form and break than others. And you'll see here with the third bullet point that those 2 vocab words are inversely proportional. We know what that means. As one is bigger or longer, the other would be smaller. So what does that mean? If we have let's picture this. We have 2 people and they're holding a rope. And then we have 2 people down here and they're holding a rope here. You can imagine these people down here have a shorter rope, obviously, or we would say a shorter bond length. And these people have a longer bond length. If you were trying to hit the rope out of their hand, if you're trying to karate chop right down the middle of these ropes, what do you think you could karate chop easier? What would take less energy to karate chop? Hopefully you're saying this would take less energy. This would not be as tight or as strong as the bottom one. I could karate chop right down the middle here and probably get the rope out of someone's hand, or at least make it a little flimsy in the middle. I don't need a ton of energy to do that. So the longer the bond length, that's less energy. If 2 people are very close, like at the bottom, they're keeping that really tight, I could probably karate chop that and not much would happen, right? It would stay pretty taut. So a shorter bond length, I need more energy to break that. That's why these 2 are inversely proportional. Okay, we have something called the octet rule. Octet, if you had to think of a number that comes to mind with oct, I'm thinking octagon, 8. Octet rule has to do with the number 8. And this is saying that when you're forming compounds in the real world, they tend to form so that each atom has an octet, or 8 electrons, in its highest energy level. That, again, is the reason why group 18, your noble gases, do not react. They don't want any electrons. They don't want to give any electrons up. Their valence shell is full. Why? Because they met the octet rule already. Recall, group 18 has 8 valence electrons. They met this rule. They're good. So 8 is the number. Now, there are exceptions to every rule. Some elements are just happy with less than 8. There are some exceptions at the bottom here that you should know because you will see them. This is not an all-inclusive list, though, that there are more out there, but we just won't see them often. So examples here, boron and aluminum can have 6 valence electrons. I have 3 bonds there. We're going to see that 1 bond is 2 electrons. So that's why I have 3 bonds. Hydrogen is happy with 2. With 1 bond anyways, it shares 2. Helium is another one. Helium, if you look at your periodic table, helium is in group 18. So you would think it has 8 valence electrons. But that's not true. Helium's atomic number is 2. So it only has 2 electrons to begin with. So helium is happy with 2 electrons. So add that to the list, helium. And then sulfur and phosphorus, they can have expanded valence shells, it's called. So they can have more than 8. So boron and aluminum can have less than 8. Sulfur and phosphorus can have more. They can have 10 to 12 electrons. They don't have to. They can have 8, but they're also happy expanding depending what they're bonding with. So we're headed to what's called Lewis structures. This is the very basic step to that. It's called electron dot notation. And all this is, it's a notation that shows how many valence electrons an element has. Instead of just writing the number, instead of just writing helium has 2 valence electrons, here are the steps. We draw the element symbol. Excuse me. To draw the symbol. Excuse me. Determine the number of valence electrons. Look at the group number. I see helium's in group 18, but I know it's an exception and it has 2. Place dots around the symbol, 1 on each side before pairing up. So here's how we do this. We start at the top of helium. We place 1 dot. That means 1 valence electron. We move clockwise. 2 valence electrons. I'm finished. It only has 2, so that's all I can show you. That's the electron dot notation for helium. Very simple. Here is borons. Notice boron's in group 13, so it has 3 valence electrons. I'll do it for you up here. We start at the top and we move clockwise. We're done. Fluorine is in group 17. It has 7 valence electrons. Again, you start at the top and you move clockwise. When you get around the entire element, the 4 sides, now you can group up or pair up with another valence electron. So this has 7 total. I only used 4. So here's 5, 6, 7. Now I'm done. Again, the most you would ever have would be 8. So for example, neon, 1, 2, 3, 4, 5, 6, 7, 8. And that's the most you would have.